In this video, we're going to talk about sequence. By definitions, a sequence is a functions whose domains is a set of positive integers, meaning that it's a function from the set of positive integers to another set. So you may ask, why is it functions or definition related to the notation sequence? Well, given a sequence using functions, meaning that you have to associate with each positive number n an element inside f that you denote by fn. So for example, you have to associate 1 with f1, 2 with f2, 3 with f2, etc. And this now actually looks like a sequence of elements in X. And we call these elements the terms of the sequence. And because each term is related to a positive number, then you can actually tell about the position of a terms in the sequence. So for example, f1 is called the first term because it is related to the first number, the first positive integers. And then you have the second term, f2, the third term, f3, and so on, the fourth term, the fifth term, and the nth term in general. Now, to ease the notation, instead of writing each term as f1, f2, etc., we can use the sequence notations using a letter a and indexed by positive integers. Now, the first term is written as a sub 1, the second term is written as a sub 2, the third term is written as a sub 3, and so on. You might use any letters you want to. Instead of using A, you can also using B, B1, B2, B3, B4, B5, etc. And now the integers become the index of the sequence. And an index actually tells us about the position of the terms inside the sequence. So say for example you have B 2021. It means that it is the 2021th term of the sequence. And if you want to find out what is that, then you have to compute f of 2021 using the definition of the sequence that you are given. Okay, so for that reason, a sequence might be given by a specific formula. That is a very frequent way to give functions. Okay, so in this example, we consider the function f from the set of positive integer into R, setting n to 5 times n minus 3 over n squared plus 1. Then use that formula, you can determine any terms in the sequence. So for example, the first term is f1. If you want to compute that, you substitute 1 in the algebraic expression, find n minus 3 over n squared plus 1. And then what you get is f1 equal 1. And you can do the same thing for f2. Substitute 2 in the expressions and compute. And then you get f2 equals 7 over 5. Similarly for f3. And then you get f3 is equal to 12 over 10. And so on. And because you can also use the sequence notation, then an equivalent way to of writing this is that you use an inside the curly brace equal to 5 times n minus 3 over n squared plus 1 inside the curly brace. Okay, and so from this you can also actually tell us a1 is equal to 1. The same for a2 is equal to 5 times 2 minus 3 over 2 squared plus 1, and this is 7 over 5. And similarly for a3, and you still get 12 over 10, and so on. So these are actually equivalent way of giving a sequence. And because a sequence, well, it's actually a sequence, a list of numbers, right? And then you can also you might also have a sequence which is listed, and of course it is listed using some kind of patterns, because a sequence might be infinite. So actually you need to have patterns in order to determine a specific terms in the sequence. So for example, here you have 1, 2, 3, 4, 5, etc. So the first term is 1. and the second term is 2, the third term is 3, the fourth term is 4, and then so the pattern is clear enough to help you to determine that the n term should be n. So using the formula that is equivalent to giving an is equal to n for all n positive integers. And similarly, if you have 1, 3, 5, 7, 9, then here the pattern should be this is the sequence of odd positive integers. So Bn should be 2 and -1. And similarly, you have the sequence of 1 over 2 power n that is listed by 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, and etc. So the dot 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 mean that now the pattern should be clear enough for you to determine the successive terms of the sequence. So say for example the next term after 1 over 32 should be 1 over 64 and so on. Well, because a sequence is a sequence, you might use sequence to keep track of information. So in this example, we choose that the amount of money on the saving account after n years, provided the initial money is $1,000 and the annual interest is 7% compounded annually as the sequence of interest. Okay. Meaning that the nth term of the sequence should be the amount of money you have on your saving account after n years. So the first term should be 1,000 plus the interest, which is 7% times 1,000. And so this should be 1 plus 7 over 100 times 1,000, meaning it is the product between 100 and 7 over 100 times 1,000. Well, so that is actually $1,070. And so after 2 years, you might get A2 equal to 107 over 100 times the money you have after 1 year. And so on, after n years, you can actually tell the amount of money you have on your account after n years using that money, that amount of money you have after n minus 1 years. So this is actually the way to give a sequence using a recursive formula, meaning that first you need to define some initial terms, and then after that a general terms might be given using the terms preceding it. So the rigid definition to a recursive formula sequence give us some examples. For example, here you might define f1 to be 0, and then you have f2 to be 1, and then after that for n greater than 2 you can define fn to be the sum of fn minus 1 plus fn minus 2. This sequence is very famous, and it is known as the Fibonacci sequence. And we have another sequence given by f1 equal 1, and then after that as n is greater than 1 you can define fn's using fn minus 1, and the specific formula in this case is fn is equal to n times fn minus 1. And so you may ask, how can you determine the real value of fn? So for that, note that fn minus 1 is actually n minus 1 times fn minus 2. So fn should be n times n minus 1 times fn minus 2. And so you do the same thing again, and you will get the final result is n times n minus 1 times etc. times 2 times 1. It is the product of the first n positive integers, and this product is very important, and we come across this very frequently. Then we give it a specific symbol for this. That is called the factorial symbol, n factorials. And when you say n factorials, you mean that is the product of the first n positive integers. So the definition for factorial symbol is that you can define the factorial symbol for any non-negative integers, not only positive integers. So for n is greater than or equal to 0, you define n factorial to be 1 if n is equal to 0 or 1, and it should be the product of the first n positive integers given n is greater than or equal to 2. Now, because a sequence is actually a function, then you can talk about the graph of a sequence. It is actually the graph of the corresponding functions. So for example, now if you have a sequence given by the formula a1 is equal to n squared over 10, then this is actually the functions f that send x positive integer x to x squared over 10. So this actually is similar to the quadratic functions. Okay, so the graph of this sequence, well, should look like a parabola. Only that you will not take every point of the parabola. You only care about the point which the x coordinates is positive integers. Okay, so here is a list of some first terms of the graph. So you have 1 and 1 over 10, etc. And here you have 5 and 2.5 at the coordinates corresponding to A5. Okay, so this is how you can graph any sequence using the corresponding functions. Now we talk about summation notations. Well, why do we have to introduce summation notation? Because we might use a sequence to keep track of the money that you spend on day end of some trip, for example, when you are away for a trip, and then you want to know how much money you spend on a day, and then keep track of that, and then you can manage the money for your trip. So you might ask, how much money have you spent after 10 days? Right. So after the first 10 days, the amount of money that you have spent is given by the sum of A1, A2, etc. up to A10. And then if you write it down, all the tens, all the terms like this, it is very lengthy. Okay. Another way to write it down is using pattern. You write A1 and after that A2, and then you use dot 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 to represent the pattern, meaning that you will take A1, A2, A3, etc. up to A10. But it is still quite long to write it down, and so it is why we use summation notation. We will write it as the summation of AI for I running from 1 to 10. That is called the summation notations. Okay, so the exact definition to the summation notation should be, if you have a sequence an, then we denote the summation of ai, where I run from 1 to m, is actually the sum of a1, a2, etc. up to am. It is the sum of the first m term of the sequence. So, for example, if you take the summation of 1 over k, for k running from 1 to m, it should be 1 over 1 plus 1 over 2 plus etc. plus 1 over m. And similarly, if you take the summation of k factorial, where k runs from 1 to m, it should be the sum of 1 factorial plus 2 factorial plus etc. plus m factorial. And well, it's might be now natural to introduce the product notation too. So instead of computing the first m terms of a sequence, you may ask, why not compute the product of the first m terms? So we might denote the product notation as follow: the product of ai, where I runs from I to m, from 1 to m, is actually the product of the first m term of the sequence. So for example, you take the product of k, where k is runs from 1 to m, it is actually the product of the first m positive integers, and it's actually m factorial, the notation that we already introduced previously. And then the product of 1 over k, where k runs from 1 to m, is actually the product of 1 over 1 times 1 over 2, etc. times 1 over m, and it is actually 1 over m factorials. Now we talk about some properties of sequences and summation notations. Given a sequence an and a real number c, then we have that if you take the summation of cai, where I run from 1 to k, it is equivalent to compute first the summation of ai for I from 1 to k, and then after that you multiply this summation with c. We can actually see that easily. So using the summation notation, you know that the left hand side of the equation is actually the sum of c times a1 plus c times a2 plus etc. plus c times ak. But then c is a common factor, then you can take it out, and it is actually equal to c times the sum of the first k term of the sequence. And now using the summation notation again, you get the property that you want. The next property is that if you have two sequences, an and bn, then you can actually tell how to compute the sum of two summations. If you take the summation of ai plus bi, that is actually equivalent to first taking the summation of ai, and then after that taking the summation of bi, and then you take the sum of the two resulting number. And then you can also prove that easily. Well, so first of all, the summations of ai plus bi is actually the sum of the first m terms of the sequence a1 plus b1, a2 plus b2 plus etc. plus ak plus bk. And then because you see that the addition of numbers is associative and commutative, you can regroup them into a1 plus etc. plus ak plus b1 plus etc. plus bk, and then use summation notation again. And now you should get the summation of ai plus the summation of bi, and then you get the properties. And similarly, now you should be able to get the third property, saying that well, now instead of taking the sum of two sequences, you can take the difference of them, meaning that if you take the summation of ai minus bi, and it is the same as first taking the summation of ai and then minus the summation of bi. And you can also have the general summation notation of ai, where I run from k to m plus k, where k might not necessarily be 1, right? And it is actually the difference between two summation notation that we already introduced. So the summation over k to m plus k is same as first taking the summation from 1 to m plus k and minus the summation from 1 to k minus 1. Meaning that you only keep the terms from k to m plus k. Okay, so now you have some formula for sum of sequences that we might use very frequently. So first of all, if you take the sum of a constant sequence, meaning that every term is c, then the sum of the first n term of the sequence is c times n. That is very easy to see. The second is the sum of the first n positive integer is given by n sum n plus 1 over 2. And if you take the sum of the first n square number, then the formula is n times n plus 1 times 2n plus 1 over 6. And we also have the sums of the first n cubic of positive integers, which is n times n plus 1 over 2, and then you take the squaring of this. We can actually prove each and every formula given here, but for that we need mathematical induction. So we have to postpone the proof until we introduce that definition, the definition of mathematical induction. Okay, so now let's take a look at an example. Assume that we have to find the sum of the following sequence. So the sequence is actually ak is k squared minus 7 times k plus 2, right? So here you need to find down the summation of that terms where k runs from 1 to 24, or equivalently you have to find the sum of the 24 first terms of the sequence. We are using the properties that we already introduced. This might be easy to see. Okay, so first we have so each terms in the summation is actually the sum of several terms. So in this case we have the sum of 3 terms, k squared minus 7k or n 2. Then we can break the summation into 2 smaller summations, meaning that you first compute the summation of k squared and minus the summation of 7 times k and the summation of 2. So now using the formula given for the summation of the squaring of positive integers, you know that the first summation is 24 times 24 plus 1 times 2 times 24 plus 1, and then divided by 6. And the second summation, because in this case 7 is a common factor, you can take it out, and then you take the second number as 7 times the summation of k, and the last sequence is actually a constant 1. Then because we have 24 first term, then the result should be 2 times 24, and so you can compute this easily and get the final answer, which is 2848. Well, to review what we have learned so far about a sequence, you might now pause the video and try to solve the following problems.